Let's come to fission. Fission reactions are of two types. One is spontaneous and other is induced. Spontaneous is no external agent is needed to for the fission to occur. Other is induced, where mankind uses the fission reaction, and the use of fission reaction can be in nuclear power station bombs, of course. But why the energy is released in case of fission reaction? Now, a nucleus is made of protons and neutrons, and these neutrons and protons must be bound in order to have a nucleus. We can plot the binding energy of all the nucleons with respect to the total number of nucleons inside the nucleus. A binding energy is a negative quantity, and as we go downward, the binding energy is increased. That is, the more negative is the binding energy, the nucleons are more bound to the system. Why the energy is released in fission? The answer lies in the binding energy per nucleon versus total number of nucleon plot. In the x-axis, we have plotted total number of nucleons. In the y-axis, this is binding energy per nucleon, and this is of course in the unit of MeV. As binding energy goes to the higher value, that means when it is more negative, the system is more bound. For example, for iron, it is somewhat iron Fe equal to 56. For iron A equal to 56, it is somewhere lying here, and it's the most stable nucleus on Earth, and this has the binding energy of almost 8 million electron volt per nucleon. If a bigger nucleus, for example a uranium fizz, that is splits up into two smaller fragments, which means for smaller fragments the A value will be decreased in this direction, and in this direction, if we walk along the binding energy graph, then we can see that the binding energy is becoming more negative in this left hand side direction. So splitting up into two nucleons, that means binding energy is increased for this reaction. So when the bigger nucleus splits up into two smaller one, because of the formula E equal to mc square, as the mass is reduced, this M is converted into some energy to increase the binding energy of these smaller fragments. For example, if we take the fission reaction for uranium, where a uranium 92-235 is hit by this thermal neutron. Thermal neutron means it's a slower neutron, it's a low energy neutron, and it's the uranium is splitting up into a krypton with 92 nucleons and barium, which contains 141 nucleons plus 3 neutrons, and this neutron will again heat up this another uranium nucleus, and again this reaction will occur. So we need to control this heating up of these neutrons, because in case of uncontrolled fission, we get plenty of neutrons in an uncontrolled fashion, which will be again hitting the uraniums, which will liberate more and more energy. So we need to control this reaction. In nuclear reactor, this reaction is controlled, but it is very dangerous in case of atomic bomb, where this reaction is not controlled. For uranium, the binding energy per nucleon is about 7.4 million electron volt. But for smaller fragment krypton, it is lying on this side, and in case of krypton, the binding energy per nucleon is about 8.5 million electron volt. So here the binding energy difference is 8.5 minus 7.4 million electron volt, which means it's a 1.1 million electron volt energy difference for this one particular reaction, for one particular nucleon. So in uranium there are 235 nucleons are there. So 1.1 million electron volt is the energy released from one nucleon. So if we consider 235 nucleons inside the uranium, it will liberate 1.1 into 235, which is equal to 260 million electron volt. And this 260 million electron volt is released actually from a single atom. So we can estimate the number of the amount of energy, huge amount of energy released in case of nuclear reactors, and this energy is released as heat, and this heat is again used to rotate the turbines, which will in turn produce the electricity. But this is not the only way with which we can split up this uranium. There are so many ways, and there are so many ways in which the uranium nucleus can be split up into other fragments. If we plot the probability of getting the smaller fragments with the different total number of nucleons, we will get uranium can be split up into smaller fragments like smaller nuclei of total number of nucleons anywhere between 80 to 160. We will get nuclei with the atomic number between 80 to 160 for the splitting up of uranium. But the probability of getting nuclei with total number of nucleons 80 and total number of nucleons 160 is maximum, as we can see from this probability distribution. And uranium 235 can be split up with all the possible nucleons between 80 to 160. Now these products of fission could be radioactive, because if we see this stability plot between N and Z, the elements which are produced as a result of fission, that is those smaller nuclei, these nuclei will have more number of neutrons than normally the nuclei with this particular Z value would have. মানে ফিশন প্রোডাক্টের ফলে যে সমস্ত নিউক্লিয়াই তৈরি হলো তাদের নাম্বার অফ নিউট্রনসটা নর্মালি এই পার্টিকুলার জেডের জন্য যতগুলো নিউট্রন হওয়া উচিত তার থেকে বেশি. সো দিজ এলিমেন্টস উইল বি রেডিওঅ্যাক্টিভ অ্যান্ড দে উইল প্রডিউস বিটা এমিশন. Another thing comes in case of radioactivity, which is very necessary to mention. This is the half-life. Half-life is the amount of time within which a particular radioactive nucleus decays to half of its initial element. For example, in nuclear reactor, if we get plutonium as a waste product, plutonium has a half-life of 24,000 years. Now today if we have 1 ton of plutonium, then after 24,000 years, half ton of the plutonium will remain. And after another 24,000 years, 1/4 ton of plutonium will survive. But there are other materials which are having a half-life of the order of seconds. Suppose this is dubnium 261, this is a transition element. This has half-life of 27 seconds, and this has half-life of 34 seconds.